Welcome to the design of concrete structure course. So up to last class we have discussed about different properties of construction materials such as steel, concrete and all different properties we have seen. And then in the last lectures we have discussed more in details about the limit state of method. That is, we discussed different philosophies, but currently we are using limit state of method for all the civil engineering designs. So in this lecture, we will develop few assumptions of limit state of method and we'll discuss more in details. So before starting into exact philosophy of limit state of method, let's discuss about the basic elements of any civil engineering structures. So this figure you can see is a frame structure where you can see these are the one frame, this is another frame, like that all the small frames are made and entire the structure has been made. So this vertical part we call it column and this horizontal portion we call it beam, and the load acting on a slab. So basically whatever human load or live loads are there, actually it is coming from the slab to the beam, then beam to the column, and through column it goes to the foundation. So primarily load acts on a column or acts on a slab, and then slabs are actually resting on a column. Okay, so whenever loads are acting on either it may be beam or it may be column or it may be slab, anywhere there will be deflections. So I think you all of you have studied it in the analysis of structure, that whenever any loads are applied on a structure, so the beam will deflect. So we have discussed like different beams, right? If a cantilever beam is there or the simply supported beam is there, and if a load is acting at the center, the beam will deflect, right? And this is the deflected shape, something like that. So different types of so whenever loads are applied, there will be deflections. Either it may be beam or it may be column or it may be slab. So this is a typical cross section or a typical section of a beam, not section, maybe a longitudinal section of a beam. There you can see the transverse loads are acting. So now the one very simple basic question, so how will you identify that which one is beam and which one is column? So this is very much basic. Okay, because if you see both members looks like same, one is maybe horizontal and another is vertical. So that is the only difference in beam and column. So like that only can we can by looking into the member can we tell whether it is beam or column, or what is the how distinct it is beam and column. So basically in beam, if the loads are acting in transverse direction, so this is a member and loads are acting on a transverse direction, right? That is diagonally or perpendicular to the axis, the loads are acting, right? So this is, we call it beam. And if loads are acting in an axial force, as an axial force, then we call it is a column. So column, if you see, loads will be acting towards the axis of a beam column, whereas beam loads will be always acting perpendicular to the column. So in a beam you will find that the transverse loads will be acting, whereas in a column the loads will be always axial load, or sometimes transverse loads are coming, but primarily the loads will be acting on a column is axial load. So that's the only distinction you can classify whether the member is a beam or a column. Even a horizontal column also may be acting as a beam if the loads are acting axially. So it is not like vertical will be column and horizontal will be beam, but if it is based on the loading pattern. If load is transverse force, then it is beam. If load is horizontal, I mean if load is axial, then we call it is a column. So here you can see this is a beam and transverse loads are acting. So because of that, the beam will deflect, right? When the loads are applied, definitely beams will be deflecting. So this is, you can see the beam has deflected here. Similarly, and this is the dotted line is the center line of the beam, and after application of the load, you can see that the beam has now deflected. Okay. So similarly, slab also you can see slab also it will be deflection will be happening. Okay, in both the directions. So you can see this is a slab, both directions we will see the deflections happen. So now you understood there are basically how to distinguish beams and columns. So beams primarily carries the transverse load, whereas column carries primarily the axial load. Okay. So now in this module or in this chapter, basically we'll deal with how to design a beam. Okay, so beams may be having a different shape. Either it may be rectangular beam or it may be circular beam, square beam, trapezoidal beam. It may be in any shape. Okay, So in this slide, we'll show it to you different rectangular beams. So rectangular beam means the breadth and the depth will be different. So you can see breadth is less, depth is high. So typically these rectangular beams you will find in multi-story structures where beams are rectangular. So even if in our campus also maximum beams you will find in a rectangular manner. And this beam, and we call it singly reinforced beam under the positive bending moment near the midspan. What is this meaning? Now let's consider a, okay, let me draw it here. So a beam, simply supported beam here, and it is resting, so it is simply supported, and two loads are acting. One is P1, for example, acting here, another is P2 is acting here. So what will be the bending moment diagram of this beam? So bending moment diagram will be something like that. So something like that will be the bending moment diagram. Okay, so I'm sorry, but it will be straight. Okay, so bending moment diagram will be something like that. So the middle portion of the bending moment is maximum. So maximum bending moment you will find at the middle of the section. Okay, whereas the minimum bending moment you will find near to the support. So this is the section. This is just if you cut a beam at the middle, so you will get this type of section. This is singly reinforced rectangular beam under the positive bending moment. See, this middle portion is basically the positive bending moment. Right? Bending moment is positive, whereas near to the support bending moment is negative. So just whatever I have drawn, this is a simply supported beam. That's why it is 0. But if it is a fixed end, both the ends are fixed, then you will find here negative bending moment, here also negative bending moment. Okay. So singly reinforced beam means the reinforcement or the steel bar is used in only one side. See, at the bottom only reinforcement is used. Okay. Whereas if you see top also there are reinforcements are there, but this is only hanging bars. Hanging bar means basically we have to provide the stirrups also, right? You saw that stirrups is also provided in a structure. Stirrups means, so this is a beam. If you see rectangular beam and reinforcements are there, here maybe four sides, four reinforcements are there, and we provide this type of steel bars all around the bar, right? Something like that. So this is, we call it stirrup. Okay, so this part we call it stirrup. So stirrup also has to be hanged, right? So in the singly reinforced, this is a singly reinforced beam where actually reinforcements are provided at the bottom, but at the top also we provided just only because to tie the stirrups. That is the only purpose in the top reinforcement. See, now let me draw it in another figure. So this figure only. So when the beam bends, so this is the buckling. Okay, beam will buckle. Okay, let me draw it in an exaggerated manner. So let's consider here a beam, rectangular beam. Okay, and when the loads are applied, maybe some UDL or something is applied. Because of that, now beam will bend it, right? How beam will bend? Something like that. Okay, although this is very exaggerated manner, but beam deflection will be like that. Okay, so now if you see at the bottom, so this fiber, bottom fiber is subjected to compression. So this portion and top fiber is subjected to tension. Okay, why? Because if you see beams has been bent after application of the load, beam is, now this is the buckled shape of beam. Now bottom fiber, if you see, is trying to stretch, whereas top fiber of the beam is trying to compress, okay, trying to shrink. So because of that, the tension force will be generated at the bottom, whereas the compression force is generated at the top. That's why in a beam section, if you see, the bottom is subjected to tension, right? So in the earlier classes, you have seen that concrete is very weak in tension. Concrete cannot take much tension force. That's why wherever tension force is generated, there we have to provide the reinforcing bars. So that's why if you see at the bottom here, basically tension force is generated, but whereas top it is compression force. So concrete can take compression force. That is not, I mean, that is no problem. Whereas at the bottom, the tension force is generated. So tension force, because to take care about the tension force, we provide we provide steel at the bottom. Okay, but top fiber is subjected to compression. So compression means concrete itself can take much compression force. So that's why the steel reinforcement are not required at the top, whereas bottom reinforcement is sufficient. Okay, but we have to provide the stirrups also, right? This type of stirrups also we are providing in a beam. So these stirrups, if you want to provide, then something will be, some bar should be placed, right, to hang, because This you have to tie it. So that's why two hanger bars are provided. This is only for taken care of the stirrups. Okay, otherwise the main reinforcement is provided at the bottom. That's why it is called singly reinforced rectangular beam, because the reinforcement is at the bottom only, single side, singly reinforced beam. Okay, so as I mentioned, the top part is concrete is under compression, whereas bottom part is steel bar in tension. So bottom fiber you understood, right? Bottom fiber is under tension, so that's why steel bars are provided at the bottom. And this is the depth, and this middle portion we call it the neutral axis. So neutral axis means there is no stress, there is no strain at the middle. So you understood at the bottom you have here tension force, whereas at the top you have the compression force, right? So in the middle somewhere you have the zero stress. There is no tension, there is no compression. So that axis we call it neutral axis at the middle. Now this figure, if you see, this is the doubly reinforced section beam under positive shear at the moment. So I am talking about positive shear, right? So what is positive shear? Positive shear means we are talking about middle part. Okay, whereas if this column, if it is a, if the support is a fixed support, so for example if you consider this as a fixed support, okay, this you consider it as a fixed support, so this end is fixed, this end is also fixed. So if both the ends are fixed, then how the diagram will be? So diagram will be, okay, something okay, let me draw it here. So let me take another color. Okay, so the if it is a fixed end, then the diagram will be something like that. So you will find negative bending moment, and then yeah, something like that. This green color line you will find if the both ends are, both ends are fixed. Okay, so you can see this both and fixed, then this is a green color line is a bending moment diagram. Okay, so so if you see at the middle always it is a positive bending moment, whereas near to the support the bending moment is now negative. Negative means the beam will bend in opposite way. Okay, so that's why near to the support the top fiber will be subjected to compression. Sorry, so top fiber is subjected to tension, whereas bottom fiber is subjected to compression. So near to the support the beam will buckle in just opposite way. So let me draw it here. So if this is a beam, so near to the support the beam will buckle like that, something like that. So that's why the bottom fiber here it will be subjected to compression, whereas top fiber will be subjected to tension. So this section is near to the support, okay, or near to the support, whereas this section is actually at the middle of the span. So this figure and these two are actually near middle span. That's why this is doubly reinforced section, because why here reinforcement provided at the top as well as at the bottom. Now you can ask that concrete can take compression force, right? Then why we need to provide the steel? Because sometimes the load is very high on a beam, on a structure, right? On a structure the load sometimes will be very high. So when the load is very high, then then the compressive stress also will be very high, and whatever concrete is there, that may not be sufficient to take care about the extra compressive force or the compressive force. So in that case we provide steel, because steel is a very good boy, right? He can take very good tension, he can take compression also, both he can take. So in some question when the load is very high, in that case if you provide singly reinforcement, means reinforcement at the bottom, and the concrete may not take the entire compressive force, so in that case we have to provide the steel also at the top to take care about the compressive force. So bottom steels are provided to take care tension force, whereas top steel bars are provided to take care about the compression force. So that's what is written, right? See, steel bar in compression. So these steel bars are actually in compression and they are subjected to compressive force, whereas bottom steel bars are subjected to tension force. Okay, so this is we call it doubly reinforcement, whereas this is we call it singly reinforced section. Now this you can see is a singly reinforced section under the negative bending moment. So negative bending moment where it will generate. So if this is a beam, so negative bending moment will always generate near to the supports. So this green color line you can see the bending moment is negative. Just make the convention, right? The top portion is actually negative, bottom is positive. So this is subjected to negative. So if the beam near to the support will be just reverse in the sense top fiber will be subjected to compression, whereas bottom fiber is subjected to tension. Okay, so you can see that singly reinforced, so top fiber is subjected to what? Tension. So that's why the tension bar, steel bar is provided at the top, whereas here tension bar is still provided at the bottom. Okay, this section is near to the support. Okay, near to the support here. Then steel bar will be provided at the top. Okay, and this is the doubly reinforced section near to the support, that is negative bending moment, over the support, negative bending moment. There you can see that top fiber is subject to tension. That's why the steel bar in tension is provided at the top, whereas compression steel are provided at the bottom. So you have to understand the concept here, why we are providing sometimes steel at the top, sometimes we are providing tension steel at the bottom. But why, what is the concept? So this is the concept. I hope this part is clear. So everything is based on the bending moment diagram. So design is actually taken care by the bending moment and shear force diagram. So which you have developed, which you understood in the last semester, drawing the bending moment and shear force diagram. So we'll be using only those diagrams for design of structures. Okay. So this is the rectangular beam. Now T-beam. So in many places you will find T-beams are also provided. Okay, because in normal practice the beam and column both we cast monolithically in the sense beam and columns are actually casted simultaneously together. So when the slabs are casted, in the same time we cast beams also. So beam and slab in now all the structures, modern structures, you will find it is not separate, unlike last slide I have shown you only beam, right? But in reality the slab is also there at the top, and this beam and the slab both are casted monolithically means same time we casted it. So because of that, this entire structure is not a rectangular part, you can consider it as a T-beam. Okay, so T-beam we can consider it, and these are the different figures. So this first one is singly reinforced T-beam under positive bending moment. As I mentioned, positive bending moment means at the mid span this will be the section, means tension will be at the bottom, compression will be at the top. So this one is doubly reinforced T section. So here reinforcement is provided at the top as well as bottom. Okay, near to the mid span. And these two are the actually over the support or near to the support. Means at the top fiber you will find tension steel, whereas bottom you will find the compression steel. That's why concrete in compression will be at the bottom, whereas concrete will be tension at the top. This is doubly reinforced T-beam. This is singly reinforced T-beam. So I'll just quickly go through this because you understood the main concept here. Now the corner beams are actually L-shaped. So T-beam will be the all intermediate beam. So for example, if I draw, let me draw a plan. So if this is a plan of a structure, plan of a building, okay, so these are the different beams passing. You can see this is a plan, okay, and these are the different beams. So, okay, so these beams are actually T-beam, okay, T-beam, T-beam. Whereas this corner beams, if you see, this is actually L beam. So this is a L beam, this is L beam, okay, but these are actually T-beams. Because both side you will find slab will be there, this side also slab, this side also slab. Whereas in case of this one, whereas in case of this beam, only one slide you have slab, this slide there is no slab, right? So this beam we call it is a L beam. Okay, this is the L beam, whereas these middle beams are T beams. So this is the typical L beam, that is corner beams. Same process, singly reinforcement, mid span, singly reinforcement, doubly reinforcement, mid span, singly reinforcement over the support, same double reinforcement over the. Now you understood, right? So when it is over the support or near to the support, you will find top fiber is subjected to tension, whereas bottom fiber is subjected to compression. I hope the concept is clear here. So these are the L beams. Okay. Now you find slab also. So if you see at the first slide, I have discussed about the different beam column sections. Their slab is also there, right? So slab also, sometimes you will find this type of slabs will be there. Means one dimension is very less compared to other dimension. So this type of slabs actually will behave as a beam when this dimension length is very small compared to this one. Then this slab is actually behaving as a beam because one dimension is very small, other dimension is very high. So this type of slab actually we call it one-way slab. So if the so Lx by Ly means length in x direction by length in y direction, if it is more than 2, then we call it is a one-way slab. But if the slab plan is rectangular or sorry square or both or Lx by Ly is less than 2, means two dimension is almost similar, in that case we call it is a two-way slab, means bending will happen in both the axes, both the direction, Lx also, Ly also. Whereas in the one way slab, the deflection will be happening about only this axis. Okay, this is a beam action it will be happening having, and this is a one-way slab. So slabs are also classified into two parts. One is one-way slab and this is two-way slab. So one-way slab means if the deflection happens in only one direction, it means the one dimension is very less compared to other dimension, or Lx by Ly is greater than 2, then we call it as a one-way slab. If Lx by Ly is more than 2, we call it as a two-way slab. Okay, now let's discuss about the assumptions. As I mentioned that um, design is not a fixed rule-based thing. So every person has a different perspective of designing. Okay, someone may tell you safety, as I mentioned. The safety is a very comparative term. So safety is different. So my safety, I'll tell you, if if the structure won't collapse, even if earthquake happens of 10 magnitude, 11 magnitude, then also my structure should not collapse. That is my safety definition. Another person will have his own safety definition. So that's why design is a philosophical matter. Means uh, we take few philosophies. Everyone has different philosophies, so we'll standardize the philosophy and then we'll design. So currently we in this course will be more focusing on limit state methods. As we discussed earlier classes also, we have three basic philosophies. One is working stress method, limit state method, and ultimate load method. So currently modern in all modern structures we use limit state method. So in this structure, in this course also we'll be discussing beam design, column design, slab design based on the limit state method. So each method has some assumptions. Okay, each philosophy has some assumptions. So we'll discuss what are the primary philosophies of limit state of method. So before I go into the actual philosophy part, let me discuss about these figures. So what you see is very much important. You have to understand this slide. I'll take more time to explain each of the slide in detail. So make sure that you understand each and every portion of these three figure. So what is this one? This one is a beam. Okay, this is a simply supported beam. So this is a beam resting on a two supports. This is one support, this is another support. Okay, and the loads are acting. So this is how much load? Only two load is acting. P. In this case, only two load. P load is acting. Okay, here and here. So this is the same beam which I have drawn in the last slide also, and I have drawn the bending moment diagram also. Okay. So now you take a section at the middle. So if you take a section at the middle, what you will find? So this is the actual beam. Okay. So this beam section AA actually I have taken. Okay. So see here at the section AA means here I have taken a section. So this is if you take a cross section, this is the cross section, and this is a singly reinforced beam we are considering. Means the reinforcement is there only at the bottom. So if you see reinforcement is there only at the bottom, there is no top reinforcement or compression reinforcement. Okay. So now if you draw a stress diagram or strain diagram basically for this beam, how it will be. So this figure is basically the strain diagram. So if you now you understood, right? Bottom fiber is subjected to tension, whereas top fiber is subjected to compression. So when the load is applied P1 and P2 into this beam, the beam will buckle, right? So this is the buckling shape of a beam. Okay. So this is the buckling shape of a beam, and the top fiber is subjected to compression. So this is the zero stress, zero strain axis. So top fiber is subjected to compression. So this is from here 0 to it is going to positive direction. So up to here top fiber is subjected to compression. Whereas if you see bottom fiber is subjected to tension, means negative stress, negative strain. So that's why we put it negative side. Now you understood, right? Top fiber is positive, whereas bottom fiber from here it goes negative. And this is the actual strain diagram. If you connect both, so this is the strain diagram. So this figure is actually the strain diagram, whereas top fiber is subjected to compression, whereas bottom fiber is subjected to tension. And somewhere at the middle, you will find there is no strain. Strain is zero, right? So this point or this axis, we call it neutral axis, NA. NA means neutral axis. Okay. So this axis is neutral axis where the stress or strain both are zero. Bottom fiber tension, top fiber compression. Now this diagram is a stress diagram. So this you understood strain diagram, and this is the stress diagram. Now you understood bottom fiber is subjected to tension, right? Tension means tensional stress will be there. So here if you see all the tension stress, who is taking care? Only steel members are taking actually the tensions. That's why all the tension stress will be accommodated here at the steel level. Wherever steel is there, in that you will find full tension force. Whereas compression force, top fiber is subjected to compression, right? So compression force is taken care by the concrete itself. So there is no steel here. It is singly reinforced section. So all the compressive force is actually taken care by the concrete itself. So here concrete is made, as concrete is there, right? So the stress strain diagram of concrete, if you recall, the IS 456 we have discussed, right? So this is the stress strain curve. So let me draw it here also. So in the IS 456 stress strain curve of concrete, how it will be? So something like that, parabolic and then straight, right? If you just check IS 456, this is strain and this is stress axis. Okay, so this is parabolic part. Now here strain axis is horizontal, right? Here strain axis is horizontal, stress axis is vertical. But here, but in this figure we have strain axis is vertical, right? Strain axis is vertical. So that's why you just rotate this 90 degree. You just rotate this figure 90 degree and place it here. Strain axis is vertical now, so that's why this is parabolic part, and then this part will start. So this is the shape of the stress diagram. So just to understand again, I'll repeat you. So first portion, top fiber is subjected to compression, right? That's why from above neutral axis, this is the stress strain. This is the stress block. Okay, stress block is parabolic up to certain extent. So up to certain extent parabolic, then straight line. So then straight line. So parabolic and then straight line. Okay, and this is the stress for the steel. So entire tension force is taken care by the steel. So entire steel stress will be a single line here. So this is the typical rectangular section, beam section with stress diagram, sorry, strain diagram and stress diagram. So I hope this is very much clear to you, because this is the basic concept or basic fundamentals of so the beam design. So now these are the different 6 assumptions in the limit state of method. So what is our first assumption? First assumption is plane section normal to the axis remains plane after the bending. What is the meaning? Meaning is that this is a section, right? So we have taken a section. So this is a beam, the loads are acting. So after the load, beam will buckle, right? This is a buckling shape. Now if you take section at any point of a beam, the section will be always plane section. There won't be any wrapping in the section. That we call it plane section remains plane even after bending. So that is our first assumption. Second assumption is the maximum strain in concrete at the outermost fiber is taken as 0.0035. That means maximum strain in a concrete is developed 0.0035. If you see the stress strain curve of concrete in IS 456, Indian code 456, maximum strain will be 0.0035. So maximum strain is here. Okay, so here the collapse happened, so maximum strain corresponding to here. So this value will be 0.0035. So that is as per our this criteria or this assumption that maximum compressive strain will be 0.0035. Okay, so that's why in the strain diagram also, if you see maximum compressive strain at the top is how much? 0.0035. So this is one of our assumption. Now what is our third assumption? Third assumption is the acceptable stress strain curve of the concrete is assumed to be parabolic. So if you see, this is the stress strain curve itself, because see, when you perform a stress strain experiment of a concrete block in a field or in a laboratory, you won't find the exact stress strain curve. So but if you perform many experiments, you will find different stress strain curve for each concrete block. So what code says, you can make this initial portion as a, you can assume initial portion of the concrete stress block as a parabolic, and then it is straight. So that's what it said here. That is third one. Now fourth assumption is the tensile strength of the concrete is ignored. As we discussed earlier also, the concrete cannot take any tension force, or very less actually, almost 10 times less than the compressive force. That's why in this assumption basically we are ignoring that tension force concrete cannot take. Although concrete will take small amount of tension force, but our assumption is that concrete won't take any tension force to become in a safer side. Now our fifth assumption is the design stress of the reinforcement are derived from the representative stress strain diagram as shown in the figure 23A and B IS 456. If you open IS 456 23A and B figure, you will find this stress strain curve of a concrete. Okay. So then the type of the steel is used for the partial safety factor is 1.15. So the partial safety factor for the steel is actually 1.15, code said. So whenever steel we're considering, we have to use partial safety factor as a 1.15. And last assumption, that is sixth assumption, is the maximum. This is for the concrete steel. Okay, the maximum strain in the tension reinforcement in the section at failure shall not be less than, this is the value where Fy is the characteristic strength of the steel. So Fy by 1.15 es. What is Fy? Fy is the yield strength of a steel. So if you go to market, if you ask for a steel, you will get it Fe 500. For example, you purchased a steel which grade is Fe 500, for example. So what is this meaning is that Fy value, yield strength of a of that grade of steel is 500 MPa. MPa means Newton per mm square. Okay. So the Fy is, for example, here it is 500 by 1.15. 1.15 is the partial safety factor of a steel. That is also our assumption. Code said you have to use this. So by Es, okay, Es. So Fy, stress by modulus of elasticity, will give you strain. So maximum strain in the concrete is 0.0035. It is fixed for all grade of concrete, code said. Whereas for the different grades of steel, the maximum strain is different. So using this formula, we have to compute. So for example, Fe 500, Fy value is 500 by 1.15 into Es. Es is the modulus of elasticity of steel, which is 2 into 10 to the power 5 Newton per mm square plus 0.002. Some value you will get it. That is the maximum strain in a steel. Now if you use Fe 415, 415, then Fy value will be 415. Just plug in the value, compute what is the maximum strain. So maximum strain for the concrete, it is fixed 0.0035, whereas for the steel it varies based on the Fy value or the grade of steel which we are using. Okay, and based on this formula we can compute the maximum strain in a steel. So these are the six assumptions of the limit state method for the beam design we'll be using extensively. So in the next class we'll derive our theory for design of singly reinforced beam section. Thank you.